Water scarcity is usually described as a lack of rainfall, empty reservoirs, or shrinking rivers. But above every city, every building, and every home, there is another reservoir, one that has no pipes, no borders, and no storage limits. The atmosphere at any given moment, it contains an estimated 13,000 cubic kilometers of fresh water in the form of vapor. This is more water than all the rivers on Earth combined. For centuries, this vast resource has been part of the natural climate system, evaporating, moving, condensing, and falling again as rain. Today, environmental engineering is asking a new question. Can this invisible reservoir become a reliable source of drinking water produced directly where we live? Atmospheric water is not evenly distributed. Its availability depends on temperature, relative humidity, and air movement. Warm air can hold significantly more moisture than cold air. That is why tropical and coastal regions contain an enormous amount of extractable water, while arid regions require more energy and hybrid solutions. From an engineering perspective, atmospheric water is not just a climate variable. It is a decentralized and continuously renewed freshwater source. Unlike groundwater aquifers, it cannot be depleted through over-extraction. Unlike rivers, it does not depend on seasonal flow. It exists everywhere, waiting to be captured through controlled physical processes. The transition from vapor to liquid begins at a critical temperature known as the dew point. When humid air is cooled below this threshold, it can no longer retain all its moisture. Water molecules begin to bond and form droplets. In engineering, this becomes a controlled water production system. To achieve this efficiently, multiple parameters must be optimized. Heat transfer rates, airflow velocity, surface thermal conductivity, and condensation area. The challenge is not making water appear. The challenge is doing it with minimal energy and maximum yield. Atmospheric water generators, or AWGs, apply refrigeration-based condensation in a closed and optimized cycle. Air is pulled into the system and passed over cooled coils. As the temperature drops below the dew point, water condenses and is collected. But production is only the first step. The collected water is then multi-stage filtered, sterilized using UV or advanced oxidation, and remineralized for safe and stable drinking quality. What we are looking at is not an appliance. It is a building-scale water treatment and supply unit, compressed into a single modular system. For the first time in modern history, a house can become a water producer. Atmospheric systems are climate-responsive technologies. In high-humidity environments, daily production can meet a significant portion of domestic demand. In dry regions, output decreases, but this does not eliminate feasibility. Instead, engineering adapts to pre-cooling incoming air, energy recovery, ventilation. Hybrid integration with rainwater harvesting, smart operation during peak humidity hours. This transforms a climate limitation into a system design parameter. Energy defines whether atmospheric water production is sustainable. Modern systems are increasingly paired with rooftop solar and smart energy management. production cycles can be synchronized with periods of surplus renewable generation. Thermal recovery from HVAC systems can pre-cool incoming air. This creates a closed-loop relationship between water and energy, where one resource supports the efficiency of the other. This is environmental engineering at the scale of everyday life. Traditional water supply depends on long and vulnerable distribution networks. Leaks, contamination risks, energy-intensive pumping, climate-induced shortages. Decentralized atmospheric systems shift part of this responsibility to the building itself. This does not replace centralized infrastructure. It reduces dependence on it, and that changes the entire concept of water security. Atmospheric water systems are already being deployed in remote communities. Disaster response zones and high-performance sustainable buildings. As efficiency improves and costs decline, their role is expanding from niche applications to mainstream residential integration. In the coming decades, buildings will not only consume water, they will generate it. The air around us is no longer just part of the weather. Through environmental engineering, it is becoming a new foundation for resilient and independent living.